one of Arne's paper, and it shows how the abstract syntax can be seen as an interlingua, as a as a bridge between the various concrete syntaxes, where the various languages can be seen as concrete syntaxes. So again, GF is a high-level language for writing grammars, and you just need to write the grammar. You get all the other tools like tokenizer, parser, type checker for free. And as I said, one can use in order to model the gender and case agreements and other agreements in concrete syntaxes, one can use records and tables and parameters. So modeling these language-specific agreements become easier using these things. And also, because this functionality has been divided into concrete syntax and abstract syntax, the scaling a GF grammar is easy in some sense. Also, around 35 natural languages have been implemented as concrete syntaxes, and these languages can be imported as software libraries. And the library for GF this library for GF is called Resource Grammar Library, which has a lot of natural languages to be imported as concrete syntaxes. Also, we can embed GF grammars in other programs, specifically Haskell, and then we can manipulate these abstract syntax trees. This is what has been done in GFLean. So we embed grammars. We have embedded grammars in Haskell, and then we do some manipulations. Now I'll show a small GF grammar in order to make you understand how a simple GF translation program works. This is not exactly how GFLean works, but this example is here just so that the idea of translation via GF becomes clear. For example, here we have this abstract syntax called demo, and we have these constructors called n0 greater 1, which take a term of type var and produce a term of type prop. And we have this constructor imp for implication, which takes two terms of type prop and produces a type prop. So this is an abstract syntax, and it tells how the trees are to be made. But in order to see how these trees would look as strings for different languages, we create concrete syntaxes. So the first concrete syntax is called demo ing. So the demo comes from this abstract grammar, and ing is what we are linearizing it as. So demoing means like an English concretization of this abstract syntax demo. And we tell how n0, when it takes a var, how does it linearize the prop, the element of the type prop. So it takes the linearization of var and it adds the string is non-zero. Similarly, greater 1, it linearizes it as takes a var and then it adds is greater than 1. Similarly for implication, if prop 1, then there's supposed to be a prop 2 here as well. Sorry, that's missing. So this has been done for English in this example. Now we can do the same for math, for symbolic math. So n0 var could be linearized as not bracket var equals 0. Greater 1 var can be linearized as var and then the string greater than 1. And implication prop 1 prop 2 can be linearized as prop 1 arrow prop 2. Now once we have this abstract grammar and these two syntax once we have this abstract syntax and these two concrete syntaxes, we can translate statements from one to the other via GF. So this is taken from the GF shell. If we give the command pass and tell that the language that we are giving the input is in English, and then we input the string for each x1, there exists an x2 such that if x1 is non-zero, then x2 is greater than 1. And we can give the command that linearize this string in the language of math. We get the following output. And the translation process happens as such. So first of all, GF takes this string for each x1 blah blah blah. It produces the abstract syntax tree, and this is how the abstract syntax tree would look like. This has been produced by GF. And then because we know how to linearize this in the language of math, the same tree is linearized via this grammar. and hence we get this output. So this is how a standalone GF translation program works. But sometimes it's not easy to define a common abstract syntax for all the languages that you want to work upon, and then the way to go forward is to embed these GF grammars in other programs and do some tree manipulations in order to make the translation easier. And this is what we do in GFLean. So that's why for GFLean we need to use Haskell as well. Now some words on the English in the controlled natural language that GFLean takes. So we call it simplified FORDL, and it's based upon FORDL, on which the input language source is SAD, and also the NAPRO is based upon. And we call it simplified FORDL because first we started with FORDL, but then we thought we should start with a smaller subset of it, and thus it's actually a very simplified version of FORDL. And the GF implementation has already been done by Frederick Schaffer, so we took the GF implementation of FORDL, and from that we created the simplified FORDL in GF. These are the differences between FORDL and simplified FORDL. So FORDL is rich in the sense that one can add any number of left adjectives in front of a noun. So one can say X is an odd, non-negative, blah 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 prime integer, but in simplified FORDL we just have we can just add one left adjective. So in order to say the same thing, we would have to split it into different sentences, like X is an odd integer, X is non-negative, X is prime. FORDL also has conjunction of predicate lists, so we can say X is odd and greater than 4, but in simplified FORDL we would have to split them in different clauses. So X is odd and X is greater than 4. Same for conjunction of term lists, so we can't, in simplified FORDL we can't say X and Y are odd, we have to split the terms. Another thing is FORDL is dynamic in the sense that the user can add on to the lexicon while working with FORDL. So there are ways to add words to the FORDL dictionary. You can define your own nouns and adjectives. But currently I think it's not possible to do it via GF, although Arne has told me that a more dynamic version of GF is in production, so it will be possible later to add to the lexicon during runtime. And the last is the macro level grammar. By macro level grammar we mean how sentences come together to form paragraphs and how the whole document is structured. So for FORDL it was structured, it was geared more towards SAD, but since we are working with Lean, we try to follow how documents are structured in Lean, like how example proofs and then definitions, how a document is structured in Lean. That's how we have structured simplified FORDL, although it's not much because currently simplified FORDL is very small, so we can't say that it has been structured to the most extent, but that's what we want to do. We want to focus on Lean. Now I'll go in detail telling about how the translation happens exactly. So this is the whole pipeline. This is the whole summary of how the translation happens. So first, GFLean takes the input. For example, here the input is every odd integer greater than 2 is greater than 1. Then, after passing with GF, we produce an abstract syntax tree for this input. I won't be showing the abstract syntax trees because they are very big, so I would just be telling that this abstract syntax tree corresponds to this linearization. For example, after passing with GF, we get an abstract syntax tree which corresponds to this natural language expression. So after getting the abstract syntax tree from GF, we do some tree manipulations, and they have been divided into two parts. So we say that we first do simplifications and then we do translations. After simplification, what happens is, for example, this sentence, every odd integer greater than 2 is greater than 1, The abstract syntax tree for this expression becomes the abstract syntax tree for the expression for every integer x6 such that x6 is odd and x6 is greater than 2, x6 is greater than 1. One thing to note here is that this sentence is a bit simple in the sense that we have added new variable names and we have kind of uh, taken out the adjectives and put them to the right, and we do this because it helps in the translation process. I'll explicitly tell what happens later, but in summary this is what happens. So we in a way simplify the ASTs, and the simplification is visible in the strings, and once we have simplified the ASTs, then translation becomes easier, and the next step is translation, so we do it via Haskell. From these simplified ASTs of the natural language expressions, we create ASTs for the Lean expression. For example, for this natural language expression, the AST for the Lean expression looks like this. Sorry, the AST for this is the linearization, the AST is there in the background, and then from the AST to the Lean expression, we go via GF. So all the steps in detail now. So the first step, we pass the input, and for that we had to write an abstract syntax and a concrete syntax for the simplified for the grammar. And because we could use parameters and records and tables, we could model the operator precedence and the logical precedence. So we could implement that star binds stronger than plus, or multiplication binds stronger than addition, and the logical and, in our grammar, the logical and binds stronger than if and if, only if. But still there are some limitations. For example, right now we haven't worked upon the concrete syntax much, and right now GFLean can take weird inputs like assume x are and odd integers. You can input this and it would not throw an error. Then we do some simplifications, and the AST simplifications, and the AST simplifications we follow some steps, like we give every unnamed entity a name, we do some variable unification, and we we change the AST such that they are in a specific form which can ease the translation process. So if we have the input as this, assume x is an integer greater than 2, then no odd integer less than 1 is greater than x. After simplifications, the AST becomes this. The AST becomes the AST for this expression. Assume x is an integer, x is greater. So we can see that the greater than 2 has been taken out and it's been used as another sentence. No odd integer less than 1, the no odd integer has been named, it has been given the name x29, and it has been, like, things are more spread apart, which helps later in the translation process. After this translation...
Sorry, can you go?
Yeah.
I wanted to... So it's a typo probably, yes?
Sorry?
So now the last x29 is greater than 2.
X20...
Oh, sorry, I'm a bit lost with the x29 and the x, sorry.
Yeah, it is a different variable. So x29 is a variable name.
Okay, so the 2 becomes x is greater than 2.
Yeah.
We play the role of 2.
Sorry?
There is no odd integer.
Yeah. No, but
So you're trying to figure out how, like, whether this translation is correct or not?
No, it's okay. Perfect. Yes. So you have the two different x.
Yeah. So x29 is the unnamed entity. So because the idea is later when we formalize, we need variable names. So we would need a variable name for when we are quantifying over no odd integers. So this variable name is introduced right now in the process. This is one of the design choices. We could have done some other thing, but yeah, this we found easy. Yes. So now once we have the simplified AST, we do the translation, and in this step we figure out how the logic and how the natural language quantifiers and how the logic is interacting with each other, in the sense that what happens when we apply no before a quantifier, and how does the implication affect the no, and how do they interact with each other. So in the previous step, we got the AST as this, assume x is an integer, x is greater than 2 and blah blah blah. After translation, we get the AST for this lean expression. One might see these H70 and also later we'll see more hypothesis variables. So these hypothesis variables are introduced later after some post-processing, and these random names are taken so that no two hypothesis variables are same. But the thing to notice here is that in this step we translate the natural language expression to the lean expression via ASTs. And lastly, from ASTs to lean expression, we wrote a small GF grammar, and using that, we converted the ASTs to lean expressions. We also do some pre-processing and post-processing. The important post-processing is like giving each variable hypothesis a unique name so that later we don't have two hypothesis variables with the same name. So this is how GFLean works. Now we also tried to test GFLean on some real life examples. So we took this textbook called Mathematical Proofs by Chartrand, Polyman and Zhang, and we took chapter 3 of the book. It's an introduction to proofs textbook, so it has like simple sentences like A is even, A is odd, and then statements about them. And we tried to formalize statements from that textbook with as little change as possible. So we could formalize 42 out of 62 statements, but we had to do some rephrasing. So the thing is that the 20 statements that we cannot formalize right now, we cannot formalize without making change to the GF grammar at all. So we would need to add terms to lexicon or have new grammatical constructions in order to formalize the rest of 20 statements. But the 42 out of 62 statements, I tried all the rephrasing that I can to formalize these 42 out of 62 statements. So we'll see
What's your estimation of how many grammar rules do you have to add? 20 or 2 or?
So lexicon would be like grammar rules, I think it would be, I don't think I can give a correct estimate. Okay, if I say 10, but I would also like change my grammar a bit. It's just not adding but also changing the existing grammar. But it's just not adding lexicon. I need to like add constructions for sets and linearize it, so it's more than adding just lexicon for sure, because otherwise I could have added the lexicon. Yeah.
And a quick question, is the book open source?
Yeah, the book is open source. Yeah, and the book is open source.
Thank you.
So I'll also show some examples from the book and how we rephrased it and what are the lean formalization in order to show what things lack, what things like how we should extend. For example, this is the statement from the textbook: if NC are odd integers, then AB plus AC is even for every integer B. So we had to rephrase it like this. So we had to split A and C are odd integers to A is an odd integer and C is an odd integer. And also we had, so the statement has a post-fix quantification. So first B is used and then B is being quantified over. Is even for every integer B. That comes after B. That comes after using B. But we had to write it in the starting of the sentence. We had to write then for every integer B, A into B plus A into C is even. Similarly for this, although for this we didn't have to change much, but still A and B integers had to be changed to A is an integer and B is an integer. One good thing is that because we modeled logical precedence in the sense that or binds strongly than if and only if, we can write the second sentence as it is with minimal change. And in the formalized statement, we can see that the or has stronger binding than if and only if.
But you had to invent the star up there, right?
Yeah, we had to. It could, yeah. We can't write just A, B to make it infer that it's A into B. Yeah, we had to write that. This is an interesting example because for this, GFLean produces two parse trees and then linearizes at two lean expressions. which are syntactically, which are definitionally the same, but the thing is, it's an ambiguous grammar. This example tells us that the grammar that I'm using, simplified Fodal, is ambiguous, and that happens because of the last sentence. It says then x square minus 2x plus 2 is not equal to 0. So so the linearization, you can see that in one lean production, the equal to is we use the not equal to symbol, and the other we have a logical not over the whole expression that x square minus 2x plus 2 equals to 0. Yes.
I'm a bit surprised by this example. It seems to me that the intermediate representation is more complicated to translate to me than the initial one. So the exercise 3.1 is let x blah blah blah.
Yes.
It's almost lean code, right? I mean,
It's almost lean code, yes. But you're saying that it's more
there is not that much natural language in the
yes.
initial statement. That's
Yeah,
what I
yeah.
realized.
Yes.
And then
Yeah, it feels more work to go from natural language and then to lean compared to you're saying, because
yeah,
there's a lot of symbolic material already in the sentence, so producing the lean code should be somehow easier, you're saying, right?
yes.
Oh, I see, yeah. Yeah. But
Is that input from exercise 3.1, like how far is that from being valid input?
so the input, this,
Like your translation, like your simplified fourthel version is very sort of heavy on the natural language.
yeah.
Whereas actual mathematics seems to be less heavy on the natural language.
Yes.
Can you handle the less heavy on the natural language?
Right now, no, we haven't, I haven't added much symbolic support except what you can see, like plus, minus, these things. So right now, no, but we want to extend it in that way so that,
Where do you see I mean, the sentence, the way it's written, maybe there's a 0 less than x less than 1, which is not integrated. But otherwise, where do you see the loss?
Well, there's more like X element R, right? Like there's just a lot more symbolism in the first sentence than there is in the natural language version in the middle.
Yeah.
And
But I mean, yes, but
sort of the first
is more. I mean,
the first one was actually in the textbook,
yeah, exactly.
right?
So
And the second version sort of looks a little bit unnatural because of too much natural language.
well, yeah. Okay. But the translation, except for the fact that you have 0 less than x less than 1, is quite faithful, no, to the first line.
In the lean version. In the lean version.
Yeah.
so in lean, can you write chained inequalities? Is it?
No.
So you need to split it into different.
I think we have to be able to parse them both. So
Somehow, and
so there's also differences in style, and sometimes you can't use the symbolic notation because there are some parts that are not symbolic. So, but I think this multiplication symbol is quite interesting because I have played with that in one grammar of formal languages. And you notice immediately that if you introduce this, then it becomes ambiguous.
Yes.
With the function application. And then, that's just how it is. So it's interesting. And I think Fortel, even though full Fortel doesn't have that for that reason.
I think this is handled by Naprosh, or maybe the rewrite of Naprosh that Matteo.
So what's the exact?
Well, this x, y, or well, maybe not in this example, but in the previous one, there was like x, y in math mode,
Yes.
meaning multiplication. And I thought you mentioned something about how math mode is handled specially, and that you
Yeah, I do handle math one especially, but right now I use juxtaposition as function application. But I could just go on to that.
Wolfram Alpha except for the multiplication.
Wolfram Alpha handles it apparently.
Yeah, I mean this is like a controversial thing anyway, right? So like this is where you get into the taste of individual mathematicians, and I never write multiplicationist juxtaposition, so this is my personal bias kind of creeping in. I think. I mean, I could do it just as well.
Normal method.
So this is another example which shows where GFLean, like what GFLean lacks. So the natural language, so the textbook expression is let xy be xyz be integers, and if exactly two of the three integers xyz are even, then 3x plus 5y plus 7z is odd. And currently this is the only way I can rephrase the whole natural language text into GFLean. So I have to split things like x is even, y is even, and z is not even, or this happens. And then it produces this lean expression. Although I would want to know what would be the ideal way to formalize this expression. Like, should we, like, if person is formalizing this sentence, should they use sets, or how would in lean how would you formalize it? Would you use like out of these 12 what does?
I mean, I would try to capture what exactly 2 out of 3 means. If you're trying to do the translation, here, right? You would want something formalish that would be equivalent to this, and rather, I mean, it sounds to me like the simplification that you did here it had to be done by hand, right?
The simplification, no, this thing, the first line to second line, yeah, that had to be done by hand, yes.
Right.
Yeah.
So like, at least you would hope that this would be done by the simplifier as, you know, that step in your process.
Yeah.
But think about having all the letters of the alphabet and saying if 25 out of 27.
No, I mean, this is also just a bad representation. If it's 25 out of 26 or n by n, certainly you want a symbol which says exactly n out of n, and you can define that symbol, right?
Yes. But this has a kind of a meta flavor here, right? You're going one level up and then using inference already to kind of.
Yeah. No, I don't think you would want to do this for.
I would formalize it as the set x, y, z intersection z alt or something like this, and then cardinality sign is equal to 2 or something like this. It's not really meta, that just sets, I mean, it's talking about a set of integers. It's not this language of piano-like stuff. So in that sense, it goes to.
In that sense, no, but it goes. You're using inference while you're still doing syntax.
Yeah.
If you want
if you do it
to,
like this,
right? That's I think the problem.
Is this exercise exactly framed this way? I'm a bit surprised of the let x, y, z in z. I would expect a typical mathematical sentence to just say if exactly 2 of the 3 integers, blah blah, and not start with the prefix.
That's exactly how it's given in the
It's
text.
surprising. So, but then I have another question. So, it's typical in a textbook, in written mathematics, that the inclusion of collections of numbers one into the other is implicit, as should be in set theory. But sometimes you go from operations on z to operations on real numbers, and then back on, say, rational numbers, because you know that this actually is a rational number, and so on and so forth. How do you handle this cast insertion in the production of the
Like coercion. So right now it
It's
doesn't.
not necessarily coercions, it's more casts, I would say.
I see. Right now, like we don't. It's more like symbol to symbol, or if it says greater, then put the greater than symbol. For example, somewhere here, maybe the last.
Yeah, you
example.
had an example, but that one
Yes.
is a bit simple.
Yeah, this one, right? Like it has R, Z, and Q, everything, and then there's greater than.
Yes.
Yeah, so right now it doesn't do anything. But I think this works in lean because there are implicit coercion.
Yeah, this is relying on lean to handle
Lean
this.
thing,
Yeah, this one is simple, but
Yeah.
sometimes there are like more subtle things that, I mean, if you're a human reader, you know that this should be a rational number, but it's not necessarily syntactically for a syntactic reason. And I don't know.
I think in a lot of those cases, there are things that have already sort of come up when lean users are trying to write down a statement and they want it to look naturally in lean,
Yeah.
and so they will have figured out some method of adding coercions or type classes or whatever in order to make it work out. And he can kind of just piggyback on that, write something that looks reasonable, and hopefully that's their interpretation.
Hence my question. I was wondering, how do you, I mean,
Yeah. So right now I don't like. I just use because Lean has that feature, so I'm just. But
it's
for
not a feature of Lean, it's a feature of the library to propose mechanisms. So, I mean, there's also, I mean, I guess my question is also Lean versus Mastiff. I mean, these kind of idioms will be specifically using formalization devices that help users to handle the statements. So I was wondering if you use such devices like casts that are non-trivial and these kind of things.
yeah, I did. So
Not for the moment.
not for the moment. Yeah. So yes. So we have seen some examples, and now we can point out the limitations. So the limitations are, first of all, the input language that we take is too simple and the lexicon is tiny. And also we accept ungrammatical sentences. And one limitation of GFLean was that currently it's not possible to extend the grammar during runtime. So the user can't add new definitions or new nouns, new adjectives.
Well, so regarding like too simple, what was the reason you simplified Forthal in the first place, right?
Yeah, to be able to to have the first thing that I can handle, like it's to start from something small and then go to the next step. That's
So do you think the next step is
for the
Forthal?
yeah.
I also think it makes sense because when you want to do the translation to logic, then you want to do it for as small a fragment as possible, and then you see the extended Forthal as a syntactic sugar for smaller one. So that's one reason, maybe not, to think about it.
I also had a question about accepting ungrammatical sentences. I'm not sure, like, I think accepting ungrammatical sentences can also be a feature. Like, one of the things that you might find annoying about using a controlled natural language is that if you don't, make your subject-verb agreement match, then it's a parse error, and then you don't get information about the actual code that you're trying to write. What's the, I mean, maybe this is a GF question, like what's the status of sort of error reporting and recovery and that sort of thing for when people write something that can be interpreted but is also grammatically incorrect, and maybe you want to tell people, oh, this is grammatically incorrect, but also here's the result.
So I think a reason to exclude ungrammatical sentences in the first place is that you also want to generate natural language, and then you don't want to get to those. But then one thing that we have tested in different projects is that you have a slightly extended syntax which allows you for parsing natural language. And then the error correction is parsing with this and then linearizing with the smaller one.
Can I add something? Because I also think that, if you have an ungrammatical sentence, you don't know what's the grammatical meaning that you meant. So, you kind of just opening a Pandora's box of all the possible things that you could.
But sometimes they are innocent, like...
that was the innocent one, of course.
This comes up in programming languages all the time. Oh, you missed a semicolon. Here, I added one for you, but maybe you didn't want a semicolon, maybe you wanted a comma, and that means something completely different. And so we're going to suggest something, tell you it's an error, but still, tell people how to proceed.
Suggestions are not always helpful.
The suggestions aren't always correct because there's definitely more ambiguity when you start parsing grammatically incorrect sentences, but did you mean X is useful?
So yes, to summarize the talk, we can use GF to build autoformalisation programs, and because how GF is structured, it's easy to scale these programs, and we have used GF to produce GFLean. A takeaway is that it can formalize 42 out of 62 statements from this specific textbook. And how we want to proceed with it, we want to make the concrete syntax better. And we want to extend GFLean's input language from simplified further to further. And also it's good to, like, you might have noticed that we are nowhere communicating with Lean in any of this whole process. And Lean is a full-fledged programming language, so maybe we can use some parts of Lean to to get the logical representation of the sentences. That's all.